Hello class, welcome to Chapter 2 of Software Testing, Tracking the Problem. In this chapter, we'll talk about how to manage problems as reported by users, how to track and manage problem reports, how to organize the debugging process, and how to keep track of multiple versions. A problem with regard to software development is any questionable functionality of a program run. It becomes a failure or defect when it causes incorrect behavior. A defect is created at the moment the programmer writes the appropriate code. However, its actual life cycle begins when some human, usually the end user or some tester, spots the defect itself or one of its effects. It becomes a feature if its effects are considered normal behavior. So for smaller programs, fixing bugs can be as simple as using your local debugger, but resolving problems for widely distributed large-scale products requires good organization and management. The life cycle of a software problem, from first occurrence to final fix, can be summarized as follows. First, the user informs the vendor about the problem. Then, the vendor reproduces the problem, isolates its circumstances, and then locates and fixes the bug locally. Finally, the vendor delivers that fix to the user. As a programmer, you may be involved in every step of the process. First as a software tester charged with finding the defects, and then as a project manager tasked with delivering the fix. Along the way, you may have to ask yourself these questions. Which problems are open? Of those, which are the most severe? Have similar issues occurred before? Will the user ever need regular updates about the status of the bug? Our problem becomes, how do we organize the entire debugging process? To do that, we'll first need to organize the reporting of problems. To fix a problem, we first need to reproduce it. Otherwise, we have no way to gather more details about that issue or know that it can even be fixed. It may become a problem just to determine exactly what is relevant regarding the bug. Real-life problems often include too much information in the form of core dumps, entire hard disks, or entire drives. And sometimes not enough, like in this example, the 1999 problem report about the GNU DDD debugger, which just stated, your program crashed, just wanted to let you know. To standardize how we report problems, and to make it easier on developers, we put the details of a problem in a problem report, otherwise known as a change request or a bug report. In that report, we have one overall goal, and that's to state all the relevant facts about the problem so the developer can reproduce it. To do that, we'd want these specific items in the report: the product release, the operation environment, the system resources, problem history, the expected behavior versus the experienced behavior, and a one-line summary. Product release is usually a version number of the program or some unique identifier. It's required so that the developer can recreate the problem with the exact version of the program as the user. It also may be the case that the problem occurs on multiple versions, so it's important to include each version that the bug occurs on. Here we have an example with the full name of the program along with the product release. The operating environment includes all the version information about the user's operating system. Problems can occur between third-party components, so it's good practice to include that information as well. Here we have an example where LimineOS 2.3 is the stated operating environment. Some problems occur only under limited resources, so information about the system's disk space, memory, and CPU are all relevant, and we include that under system resources. The problem history is a description of what has to be done to reproduce the problem as a minimal set of steps necessary, so this will also include any input files or configuration files. The goal here is to simplify the problem to its most relevant steps, but to also be thorough. If the vendor cannot replicate the problem, it cannot be fixed. In this example, there's two steps. First, create a document and attach a PNG graphic to it. The next step, print that document on the default printer. The description of expected behavior should describe what should have happened according to the user. In continuing with our example, the description of expected behavior is simply that the program should have printed the document. The description of experienced behavior should describe the symptoms of the problem. You should remain as unbiased in your description as possible, as humor, sarcasm, or insults will only delay the developers from fixing the problem. In this example, we list the contents of the stack after a crash. The one-line summary of a problem should summarize its severity so its priority can be deduced. The worse the impact on the customers, the faster a fix should be delivered.
To summarize our previous example, VPP 1.1, our program, crashes when printing documents with PNG graphics. Some programs have talkback or feedback capabilities built in so that developers can collect bug reports directly from users in standardized forms. Here we have an example of a feedback form for a plugin created by the software development company DreamCycle. In it, you can submit a bug report immediately after a crash has occurred. In most programs, when an error is detected, information about the state of the program at the time of failure is automatically collected and sent to the vendors in what is called a core dump. Log files can also be used to record the events of a program prior to a failure and help the developers trace back to its origin. When a vendor quietly collects information about the user via log files or by some other such means of recording, privacy becomes an issue. End users need to know if and what personal information about themselves is being collected by vendors. This is easy to verify with handwritten forms, but log files and core dumps may contain sensitive information about the user that they don't know about. It is important to always let the user know exactly what information you want to collect and give them the option to cancel it. Once the problem reports are collected, we'll need to manage them. One way to keep track of problems is through the use of a problem document, or problem list. This is easy to set up and easy to maintain, but only one dev can work on it at a time. Additionally, the problem history of earlier issues becomes lost, and it does not scale well. The alternative is to use a problem database. In continuing our study on how to manage problems, we will now look at Bugzilla, Mozilla's open source problem tracking software or problem database. Despite being free, Bugzilla offers many of the same features you'll find on more expensive problem tracking systems and is a perfect example of how to organize and manage bug reports for large-scale programs. Here we have Bugzilla and an example of its extensive user interface, which allows for searching and reporting bugs. A problem severity indicates its impact on the development process. Bugzilla can classify problems by the following severity levels. Blocker, also called showstopper, impedes the development or testing of the product. Critical includes crashes, memory leaks, or loss of work. Major, which indicates significant loss of function. Normal, or the standard problem, results in loss of functionality only under specific circumstances. Minor, which indicates a minor loss of function. Trivial, which is simply an aesthetic problem that does not result in the loss of any function. Or an enhancement, which is just a request for new functionality or changes to an existing one. Bugzilla also allows bugs to be classified by priority. Priority of a problem is the main factor in deciding which fixes are to be completed first and which can be completed at a later date. The priority and severity of a problem need not be correlated. Bugzilla recognizes the 5 following levels of priority. Highest, which means that the problem must be completed ASAP. High, which means that the problem should be fixed by the next release. Normal, which indicates that it should be fixed soon, depending on the other current problem's priorities. Low, which indicates that it will be fixed eventually, but it's not a major issue. And lowest, which means that it's not currently affecting functionality. Bugzilla also allows users to set problem identifiers, comments, and set up to receive notifications. Every problem gets a unique identifier, or PR number, sometimes called a bug number. This is so developers and managers can refer to specific problems in emails, log files, core dumps, etc. Developers and users should also leave comments on the bug report throughout the lifecycle of the problem. This lets others involved know about initial findings, possible causes, and suggested fixes. Everyone involved in the process can also set up to receive email notifications of bug report changes. Once a problem report has been entered into the database, it must be processed. The following graphic shows the life cycle of a problem in Bugzilla. All problems start out unconfirmed and move through the life cycle to closed. The state of the problem indicates its position in the life cycle. All new problems have an unconfirmed state. At this point, the user has encountered the problem and has reported it to the vendor. The problem is then given a PR number and assigned a severity. New problems indicate that the associated problem report is valid. That means that it contains all the relevant information and that there are no known duplicates in the system. A problem report is moved to the assigned state once the problem has been assigned to a developer. Once a problem is moved to the resolved state, Its resolution tells us what has become of the problem report. Fixed indicates that the problem was fixed normally. Invalid indicates that the problem is not a problem or that we don't have enough relevant facts. Duplicate indicates that there is a duplicate of the problem in the database. Won't fix, which indicates that the problem will never be fixed or that it might be a feature. Or works for me, which indicates that the problem cannot be reproduced at all. A problem report becomes verified once the problem has been fixed with a solution approved by management. The next step is to deliver that fix to the user. A closed problem report indicates that the newest release of the program no longer contains the problem. If a problem is rediscovered, it is moved to the reopened state rather than the new state. A good problem database is the basis for all daily work on problems and failures. If nobody files reports, it's useless. If nobody marks problems as resolved, will be quickly filled with outdated information. Problem reports need to be handled in a timely manner. But if every developer has a hand in deciding how all of these issues are handled, disorder is inevitable. In response to this problem, many organizations will create a Software Change Control Board, otherwise known as an SCCB, tasked with tracking problem reports and deciding how they're to be handled. This committee is usually comprised of the development lead, testing lead, project lead, and sometimes representatives of the client. They will assign problems to individual developers and also set problem priorities. Problem tracking databases need not only be used for resolving bugs, but we can use them to develop products as well. In this process, problems are modeled as requirements instead. The severity of a problem indicates its importance to delivering a fully functional product. So major problems are considered central requirements, and minor problems are considered optional features and have low priority. A good problem tracking system should have the ability to organize problems hierarchically. That means that larger, more complex problems should be able to be broken down into smaller, simpler subproblems. The problem is considered fixed when all of its subproblems are fixed. In problem-driven development, our initial problem is that there is no product at all, and it's finally closed when the development process is complete and the final product is shipped. A sufficiently large and well-used problem tracking database will eventually encounter a meta-problem, too many problem reports. For example, in September 2003, the Mozilla problem database listed roughly 8,300 unconfirmed problems just waiting to be assigned. One leading reason contributing to a large number of problem reports is duplicates, which we briefly talked about earlier. If a program has several users, chances are likely that they're going to see and report the same bug. So for example, user 1 could submit a bug report saying, I opened page X and it crashed. And then a second user could state, I opened page Y and it crashed. And then user 3 could state, I opened page Z and it crashed, and so on and so forth. Searching the list of reports for problems with identical causes is simply infeasible. A limited solution is to ask users to search for duplicates in the database prior to submitting a problem. That way, identical problems can be marked as duplicates, and when the original problem is resolved, all its duplicates can be closed as well. Unfortunately, finding duplicate problems isn't as easy as it sounds. This is because there are two conflicting issues when creating bug reports. First is that we want as many facts as possible in order to effectively and quickly reproduce the problem. But to identify duplicates, we need as few facts as possible in order to spot similarities. This is why problem reports should be simplified to contain only the most relevant facts. In any case, a widely used product will inevitably collect a myriad of problem reports, many of which will never be resolved. And that is terrible for any developer's morale, as every day at work they have to go through a jungle of problem reports. In this vein, we introduce the obsolete state. A problem report can be marked obsolete if it can't be fixed at all, is old and has only occurred once, or is old and has only occurred internally. Relating problem fixes to product releases is difficult. Even with the product version, having the ability to reproduce any given software configuration at any given time isn't easy. The DLLs, binaries, and tools used to create them must be consistent throughout. The solution here is to create a version control system. When a new release is shipped, we mark the source space with a tag. We then use this tag to create the source space and together create the product. Additionally, we can use a version control system to manage product evolution through branches. that has two main concepts. First, the main trunk, which houses new features that we add to the product to be added and tested, and branches, which includes only fixes and is used for stable releases. That way we can ship fixed products while also developing new features. The graphic below shows an example product using a version control system. It contains two files, A and B, with new releases indicated by the dotted line. The first release uses version 1.1 of file A and version 1.2 of file B. File B is then updated to version 1.3 and contains new untested features. If a user at that point reports a problem in release 1.0, do we ship version 1.3 of file B in the new product? No. We branch off from the main trunk to create version 1.1.1.1 of file A and version 1.2.1.1 of file B. This is where the needed fixes are going to be implemented. Eventually, we can merge branches back into the main trunk once we know it's stable and ready for the next release. It's important then to state in the problem report the specific releases a problem has been fixed in. Here we can see problem reports in the track problem database. We can see problem information as well as the specific version that the problem occurs in. As unit testing is a common occurrence in the software development process, we need to ask ourselves, should failed tests go into our problem database? Developers mainly find bugs through test cases, but there are some issues with recording tests as problems. First, tests occur frequently, hopefully, and failed test cases will just bog down the database. With automatic testing, you can quickly check test outcomes and there is no need to log them to the system. And if a test fails, you can find the defect locally and fix it immediately. Test cases make problem reports outdated, so it's always preferred to write test cases. Anything that does not translate to code can be stored as a future idea or request for enhancement through the problem tracking system. Efficient problem recording, tracking, and management is essential to the maintenance of any program, and that starts with creating effective problem reports. A useful problem report should contain only the relevant information needed to reproduce the bug. A standardized set of items can guarantee that. That includes the product release, operation environment, problem history, experience versus expected behavior, etc. The contents of the report must be well structured and reproducible, have a descriptive summary, be as simple and general as possible, and be completely neutral and factual. Products that can be configured to collect user feedback or system data on failure will always have a head start in finding and fixing bugs, but it's important to understand the user's privacy here and handle those concerns accordingly. A software change control board can be created to oversee problem tracking by classifying, prioritizing, and assigning problems so that the developers can work on fixing bugs. An integrated version control system should be used to keep track of different software configurations, keep the fixes in the branches, and new risky features in the main trunk. Once a test case has been written to identify a problem, we mark that problem report as obsolete. Creating test cases should always be preferred to writing problem reports. Although we mainly focused on the conventions of Bugzilla, it certainly isn't the only problem tracking tool out there. For example, Jira, a licensed product, is more customizable and has more features. PHP Bug Tracker and Issue Tracker are simpler alternatives to Bugzilla and have a concentration on being user-friendly. Track, which we briefly looked at earlier, is a lightweight problem tracking system with integrated version control and customer support. SourceForge provides forms, public version archives, user management, and mailing lists. And also it's available online as well as for installation at a local site. GForge, a spin-off of SourceForge, doesn't host products and is only available for local installation. And that concludes our look into Chapter 2, Tracking Software Problems. Thank you for listening.